Okay, let's dive into this explainer and really demystify the butterfly effect. We're going to move past all those pop culture tropes today to uncover the fascinating physics and mathematics that literally scale all the way from massive, macroscopic weather patterns right down to the microscopic quantum realm. We hear this term thrown around all the time, but the actual mathematical reality behind it, it is hands down one of the most beautiful and profound discoveries in modern science. We've got a perfectly structured journey for you today. We'll start with Section 1, the myth of randomness. Then Section 2, mathematics of the butterfly. Moving into Section 3, the quantum scrambler. And we'll wrap it all up with Section 4, the arrow of time. So, Section 1, the myth of randomness, where we explore that famous pop culture trope.
Right, so we've all heard the classic cliché. It was famously cemented in a 1972 presentation titled, "Does the flap of a butterfly's wings in Brazil genuinely have the power to set off a tornado in Texas weeks later?" Now, the popular imagination often views this as a literal, direct chain of events, like the butterfly is the actual engine of the storm. But in physics, this metaphor represents something far more structural. It's really about how interconnected, highly complex webs of initial conditions cascade into massive, large-scale alterations.
And there is a massive contrast to unpack here. While the public often assumes the butterfly effect just means the universe is governed by random magic or unpredictable noise, the mathematical reality is actually something called deterministic chaos. What this means is the system is completely governed by exact deterministic equations, strict rules. But the system itself is simply incredibly sensitive to its starting state. Determinism, as it turns out, absolutely does not guarantee predictability. Now, this concept didn't just pop up overnight. Back in the 1880s, Henri Poincaré realized that adding a third celestial body to gravitational math created highly complex, non-periodic orbits, which was really our first hint of dynamical instability. Then by 1950, Alan Turing noted how a displaced electron could change a person's entire fate. Fast forward to 1952, Ray Bradbury explored the timeline-altering death of an insect in his sci-fi classic A Sound of Thunder. But the whole thing culminated in a literal scientific accident in 1961, thanks to meteorologist Edward Lorenz. See, Lorenz accidentally birthed modern chaos theory when he restarted a computerized weather simulation just to save some time. But instead of entering the exact initial condition of 0.506127 from his previous run, he used a printout that rounded the number down to 0.506. That tiny, seemingly inconsequential difference, literally just a few 10,000ths, grew exponentially in the simulation. The result, a completely divergent weather scenario. Which brings us perfectly to Section 2, Mathematics of the Butterfly, where we'll look at the geometry of chaos. So how exactly does a tiny rounding error amplify so aggressively over time? Well, to quantify how fast these small differences diverge into massive changes, mathematicians use what's called the Lyapunov exponent. Imagine two almost identical starting points. The Lyapunov exponent measures the average exponential rate at which their trajectories separate over time. If this exponent is positive, small differences grow exponentially. This mathematical value literally sets our predictability horizon. It is the exact mathematical reason why your weekend weather forecast becomes a complete guessing game if you try to look 2 weeks out. Lorenz actually mapped this exact sensitivity using a beautifully simplified system of nonlinear differential equations. He built a model using just 3 core ingredients of fluid flow: convective intensity, horizontal temperature gradients, and vertical temperature profiles. These simple, totally deterministic equations, when you run them together, end up producing incredibly complex, chaotic motion. But here is where the math gets truly beautiful. Instead of just flying off into infinity, these chaotic trajectories remain trapped within a bounded geometric structure known as a strange attractor. If you plot this out in phase space, the lines spiral around endlessly without ever intersecting or repeating exactly. They form a literal butterfly-shaped fractal geometry, revealing this majestic, hidden order operating right beneath the surface of the turbulence. It's just stunning. Let's shift gears now. Section 3, the quantum scrambler, taking chaos down into the microscopic realm. Transitioning to quantum mechanics presents us with a massive puzzle. In classical physics, as we saw, chaotic trajectories diverge. But the rules of quantum mechanics just don't allow for that kind of simple exponential divergence. Instead of geometric spreading, quantum chaos is all about how information itself scrambles across a system. It tracks how a localized disturbance basically infects an entire many-body system over time. To diagnose this unique microscopic sensitivity, physicists rely on a really cool tool called out-of-time ordered correlators, or OTOCs. Think of this as the quantum analog of the butterfly effect. When a local perturbation is introduced into a quantum system, the OTOC measures how that local operator deforms into a highly complex, non-local state. It essentially tracks how rapidly information becomes scrambled and completely unreadable down in the quantum realm. Now, in classical mechanics, chaos basically has no speed limit. But in the quantum realm, physicists actually proved there is a strict mathematical speed limit on the butterfly effect, known as the MSS bound, which is dictated by the temperature of the system. And you know what physical entities actually max out this absolute speed limit? Black holes. Yeah, they are mathematically proven to be the fastest information scramblers in the universe. No way around it, that is just incredibly cool. Finally, Section 4, the arrow of time, connecting all of this abstract chaos to our daily reality. The microscopic laws of physics, like Newton's laws or the Schrödinger equation, are perfectly time reversible. If you watch a movie of a perfectly elastic collision, it looks exactly the same running forwards or backwards, right? However, deterministic chaos creates a profound asymmetry. When we try to trace a complex, out-of-equilibrium system backwards, a process called retrodiction, we fail. The extreme sensitivity to initial conditions means that without absolutely perfect, infinite precision data, predicting the future and retrodicting the past are fundamentally different tasks. And this exact mechanism is what drives thermodynamic entropy. As those positively Lyapunov exponents we discussed earlier constantly amplify microscopic unresolved variations, they push that uncertainty right up into the macroscopic world. This continuous generation of entropy acts as the physical driver behind the irreversible flow of the arrow of time. It is literally the fundamental reason why you can remember the past, but you cannot remember the future.
So, what does this all mean for us? The butterfly effect isn't just some quirk of weather forecasting, it is the fundamental physical mechanism constantly scrambling the trail of initial conditions in our universe. Because forgetting is an irreversible process in physics, it leaves us with one profound question to end on today. If chaos is constantly erasing the precise starting points of everything around us, can we ever truly know the past?